Okay, and we are on our last target for Unit 10 for Key Concept 10. This is determining the best model for the real-world problem, aka comparing linear and exponential functions. Let's start with your learning goals. I can calculate the rate of change based on information given in a graph and use that to answer a question. Identify whether a table represents exponential growth or decay. Identify the characteristics of exponential functions. Compare the graphs of a linear and exponential function and identify properties of both. And finally, complete a table of an exponential function and explain why it is an exponential function. All right, so first example. Greg needs to read a book that is 500 pages long. The graph shown at the right shows his progress over the first 6 hours of reading. If he continues to read at the same rate, how many hours total will it take for Greg to read the entire book? So the first thing we need to do is find the rate of change. So to do that, we have 2 points here that we're given. Okay, we've got 252 and 156. So we do 156 minus 52 over 6 minus 2, which gives us 104 over 4, which simplifies to 26. Now we're going to take that 26, because that's how long, he's averaging 26 pages an hour. So at that rate, we want to take the 500 pages of the book divided by 26, which will give us an answer of 19.23 hours. Second example, which of the following table models exponential growth? So we're looking for something that is increasing over time and also increasing by multiplication. Here we go up, okay, so that's good, but now we go down, so this one's no good. Here, we're going down. And we're going down by dividing, it looks like, dividing by 4. But because we're going down, no good. Okay, over here, we're going up, and we're going down. So it's not exponential growth because exponential growth only increases. And here, 1/4, 1/2. Okay, so far so good. 1, 2, 4, 8. So if you notice, now we're basically multiplying by 2. Not basically, that's what we're doing. We're multiplying by 2. So this is, in fact, our table that models exponential growth. Okay, true or false regarding functions that model exponential growth? The value of y is always greater than the value of x. That is false. So if you think about a graph with exponential growth, it goes like this, okay? This could be 5, and we might still be over here at 1, okay? So that's why that's false. The graphs are always symmetric about the y-axis. Well, if you look at a growth graph and we flipped it over, it would not match up. It would actually do this, which is not symmetrical. Symmetrical would be something like this. Okay, that's not exact, but where if I folded this over, that this would lay on top of that. Okay, so just so you know what symmetrical means, this is not symmetrical, so this is false. The value of y is always positive. Okay, so that's possible. Unfortunately, this always here is not necessarily good. If it was the value of y, a value of y can always be positive, maybe. But if I wrote a function something along the lines where we had a minus and we were shifting it up or down, okay, that one would be false. So that always is what throws that one off. The range depends on the growth factor. No, it doesn't, because the range is going to, now granted, how quickly it goes up depends on the growth factor, but the range is still going to be, unless we put a limit on it, the range is still going to be what it's going to be, so that's false. And then finally, the value of y decreases as x gets more negative. So again, if we look at something that's exponential growth, okay, so this is where y is increasing, but x is also increasing. If we go to where x is decreasing, you notice that y is slowly going down, so that one is true. All right, example 4. A local newspaper has projected that its monthly online revenues in thousands are growing at a rate modeled by f1, which means function 1, don't worry about that, of x equals 1.72 to the x power, while its monthly print media revenues only increases at a rate of f sub 2 to the x of x equals 58x plus 58. They give you the graph. We give you the graph here. We want to shade the region where the print media revenue exceeds the online revenue. So the print media was this formula, which is this. So we want to shade the area where it's more than the other one, which is right in here. Okay, so we would shade in there. Now, at what dollar amount would the online imprint revenues be equal? That's going to happen right here. Now, just by looking at this, notice there's no labels on this or anything, so it's going to be hard to tell which one's which as far as like an exact point. And notice I have an exact answer here, $769. What you're going to do is you're going to have to do this on the TI Inspire. So you're going to enter two functions. You'll enter this function. So you'll start a graph, you'll enter this function, hit tab, enter the next, or press down arrow, enter this function. Okay, and then you'll come up with a graph. Then you'll have to zoom out until you see your graph looking like this, and then look for an intersection and label that. And I'll just show you how to do this in class because that'll be a lot easier. If you really are that curious, just look up TI Inspire determining point of intersection. You should be able to find something online. All right, and finally, example 5. A certain type of plant grows new leaves each week. The table below shows the number of new leaves in each week. Complete the table. So we need to figure out what's going on. So here's the number of weeks. Notice these are going up by 6. So I'm going to show you something that would be a common mistake to make here. So here we're multiplying by 6 to get each one. So to get 4, all I have to do is multiply by 6. Get 1296. All I have to do now again, multiply by 6. Get 776. Okay, now here's where the mistake is. You might want to just keep going and multiplying by 6. Unfortunately, notice what these numbers are. 10 and 20. So what you need to do is back up there. You'd stop right there. You're not multiplying by 6. We need to figure out what the formula is, and it's just as simple as 6x. Okay, that's all it is. So just do, plug in y equals, or not y equals, just on your calculators, just hit 6 and then your caret key and then to the 10th power. You're going to get a really, really big number. I'm not going to be able to fit it all in here. It's like 604,661,76. So that's 60,466,176. And then when you do that again to the 20th power, that's an even larger number, basically 3.65 times 10 to the 15th. Okay, when you see the E, that's the same thing as this. Your numbers should be more manageable, but just to let you know that's what you do. I wanted to show you what most people, if they make a mistake on this part, would do, and that's this right here, and just keep multiplying by 6 without paying any attention to what's going on here. So put those numbers that I said first, okay? And then this should actually be B, not C. Determine if the graph of the function represented by the table will be linear or nonlinear. Well, that should be easy. The graph is nonlinear because it models exponential growth, where you're multiplying by 6 each time x increases. And that is it for this key concept, guys. You have a lovely, lovely day or evening or whatever it is that you're watching this in. And if you have any questions, please do not hesitate to let me know. And I will be happy to answer them and get you on the right path. Take it easy, guys.